there! Let me introduce myself. I am the Weather Wizard. I understand the weather more than anyone. Today, I'll be talking about techniques in weather forecasting and data assimilation. Have you ever seen a weather forecast on television? Apart from the day-to-day information, weather forecasting acts as a real lifesaver. It is especially important during extreme weather events, such as tornadoes, hurricanes, flooding, and severe winter storms. Weather forecasting is also used in areas such as commercial shipping, offshore oil and gas exploration, agriculture, and power generation. Do you have any idea how weather forecasts are made? Let me explain. Before cutting-edge technologies, such as supercomputers, weather forecasts were produced manually. Forecasters drew weather maps of the current state of the atmosphere and used them to predict how the weather would evolve. When computers became advanced enough, we began using mathematical models. These models of the atmosphere predict the weather based on the present weather conditions. This method is called numerical weather prediction. This is Richardson. He is considered the father of numerical weather prediction. What Richardson proposed was to divide the Earth into a grid of atmospheric boxes. Then, apply a set of mathematical equations which approximates the evolution of the atmosphere to each of the boxes. This will depict how the atmosphere evolves. Once you put together all the results of the various boxes, you will get the forecast for the entire globe. Richardson developed this idea during the early 1920s, before computers were invented. Therefore, all calculations had to be performed manually. He also came up with an idea for a forecast factory. This figure is an illustration of his forecast factory. It shows a large theater with 64,000 human calculators. Their job was to help predict the weather. After the advent of the computer era, the first numerical prediction was performed by an ENIAC digital computer. This occurred in 1950 by a team led by Jules Charny. In modern days, computers are so powerful that millions of calculations can be performed in a short span of time. As a result, weather forecasts have become more accurate, with fewer numbers of false alarms. As already mentioned, weather models are based on a set of mathematical equations that are derived from laws of physics and fluid motions. By solving these equations, we can see how the atmosphere evolves. In order to provide a starting point to the model forecast, we need an initial guess of present weather conditions. In other words, in order to know the weather conditions of tomorrow, you should input the weather conditions of today. The present weather conditions are called initial conditions. The initial conditions are defined by a set of atmospheric variables, such as wind speed and direction, temperature, moisture, and surface pressure. Suppose you want a forecast of the weather over the United States. Inside the weather model, this area of interest is divided into a fixed number of regularly spaced locations called grid points. The star represents a grid point. It should also be noted that the grid points are not only distributed horizontally, but also vertically. Each of these grid points carries information about the wind speed, temperature, and moisture of that particular location. The distance between the grid points is what gives us the resolution of the weather model. The larger the separation between the grid points, the lower the resolution will be. Higher resolution means you need a larger number of grid points. More grid points means more computations. Therefore, high-resolution models require more computer resources than lower resolution models. Let's say that today is Sunday and you want to know what the weather will be on Monday. To find the answer, you plan to run a weather model in your computer. Once you start running a weather model, it uses the weather conditions on Sunday. It then performs computations with the help of the computer in each of the grid points to generate the forecast for Monday. Now that you know what the weather will be on Monday, you can use this information to forecast the weather on Tuesday. This continues like a chain. But why is the weather forecast sometimes wrong? Weather forecasts can go wrong due to the errors in the initial conditions or uncertainties within the weather model. The weather models are extremely sensitive to the initial conditions. Extremely small errors may grow and amplify with time. Therefore, it produces a very different evolution of the weather system. For instance, imagine there is a hill with a ball on the top of it. If you give it a small push in this direction, the ball will roll down and fall on this side of the hill. This time, let's give the ball a small push in another direction. Now the ball ends up on the other side of the hill. A small change in the direction of the push makes a large change in the location of where the ball lands. Let me explain that another way. Consider this red line is the truth. Let's assume that there is a small error in the initial conditions. The blue line is the forecast. See how the forecast evolves with time when there is an error in the initial conditions? The truth shows that tomorrow is a sunny day, but due to errors in the initial conditions, the weather forecast shows a cloudy day. How do we fix this problem? One method is to use observations to correct the forecast and bring it back closer to the truth. Using observations to correct the model forecast is called data assimilation. The observations represent values closer to the truth. Where do these observations come from? Radiosondes from weather balloons, satellites, ocean buoys, ships, and airplanes are all sources for the observations. How do we use these observations to correct the model forecast? Suppose there is a radiosonde observation which represents the temperature value over Colorado. It is represented by the red dot in this figure. We use some mathematical techniques to best combine this temperature observation with values in the grid point. This corrects the temperature in the grid point to make it closer to the truth. The corrected grid points are shown in red. And that is how weather forecasts are made. I hope you now have a clearer understanding about weather models and the data assimilation processes used in them.